Okay, hi again, guys. So this part two video, okay, I will show you, I will explain you on some more of the RTD function and also some example. But before I do that, okay, so some throwback of what we have learned in the first video. Okay, we did go through the what is RTD, which is ET, and then what is mean residence time, TM, right? Okay, so we also went through on the variance. What is variance? So how to describe variance? This is what I use in my lecture notes, but in your book, this is the one that's stated in the book, in your textbook. Okay, where T bar is actually your TM radians, your main residence time, right? So skewness, I skip first the skewness because there's none of this in your book, right? So again, for the pulse input, all right, so earlier I did mention on the pulse input experiment. Okay, so tracer will be injected at this part, okay, and then into the fluid entering the system. Okay, so it will be injected as short time as possible to ensure that the RTD is accurately measured. Okay, and then the outlet concentration will be detected here. Okay, and then this will be recorded as a response curve, as what you look at here, where this is what we call response curve, where CT versus T, then you see there is the curve, right? So ET, okay, can be described as in this function. So ET can be described as QCT over M. Okay, earlier we have this as ET. Okay, in the previous video part 1. Okay, so I want to show you ET also can be calculated using this formula, right? So ET is equals to QCT over M, where Q is actually the flow rate and M is actually the amount of tracer. Okay, so M is equals to the integration of QCT dt from 0 to infinity. Okay, so bear in mind, sometimes we cannot measure M directly. Okay, like, okay, you inject, let's say, 10 milligram per liter, sometimes it won't come out as 10 milligram per liter. It will not be the same because sometimes it will absorb in the rectum, right? So that's why we use this formula to describe the total amount of tracer that being used, right? So combining these two equation, okay, so this equation QET equals to QCT over M is actually equation 5.13, okay, in your book. Okay, so this is equation 5.13 in your book, right? And then when you combine these two, okay, these two equation, then it will give you an equation of ET equals to CT over the integration of CT dt from 0 to infinity. So this is the similar as the one that we learned before, right? Okay, so let's have a look on the example. Okay, example 5.1 from your textbook. Okay, so in this example, okay, given the regenerator in the fluidized catalytic cracking unit combust coke on silica alumina catalyst with air to regenerate the catalyst. Okay, the flow rate of air entering the regenerator is 0.84 kilomole per second. So this is actually your Q, right? So this is actually your Q. RTD of air in the regenerator is determined by pulse experiment. So this is another keyword with helium as a tracer. Okay, the amount of helium injected is 8.84, 10 to the power of minus 3 kilomole. So this is actually your M, right? Helium concentration C, as indicated by the molar ratio of helium to other gases in the effluent of the regenerator, is measured as a function of time, as shown in this table. So they inject at time 0, it produce your concentration 10 to the power of 6, 0, and then so this is the recorded data. So the question want you to determine the RTD density function, okay, the RTD density function, and RTD function at time t equals to 35 seconds. So in other words, they want you to determine the RTD function, which is ET, right, at t equals to 35 seconds, right? So in this data, okay, you can use the earlier equation, this equation 5.13, okay, to solve this, okay. So you need to convert, okay, from this data, data that have time and concentration, convert it into time and ET. So how do you convert this CT into ET? Is by using this equation 5.13. Okay, so Q is given 0.84, right? And then CT, you take CT at every point, okay? And then M is also given as 8, okay? M is 8.84, 10 to the power of minus 3. Okay, so you calculate back and you will get this kind of ET. So when you plot the graph, okay, something like this, when you plot this point, okay, in a graph, okay, so you will get a curve like this, okay. So the question wanted to ask you what is the ET at t equals to 35 seconds. So this part actually, so it is actually the area under the curve. That's why they you need to calculate the shaded area, okay, from 0 to 35. So that is your ET, right? So the final answer for your ET will be let's have a look on the book. Okay, if written here, your ET would be for 35 seconds, all right, it will be, I think, 0.523. Okay, so that's the value of your ET, right? So let's go for the next example on example 5.3 in your book. Okay, so this is a bit more complicated compared to the previous one, right? So for, okay, this one, okay, they want you to calculate, okay, RTD in a constant flow reactor was measured using the pulse, again, pulse input reactor, okay. So this is the keyword. The relationship between effluent tracer concentration CT and T is listed in the following table, okay. This data are given to you. Okay, calculate the mean residence time, okay, mean residence time and variance, okay. In this case, mean residence time, if you follow my the symbol that I use in my slide, is actually TM, but in your textbook it's actually T bar. All right, the formula is the same. Okay, variance, we use the same symbol, which is sigma square, right? So now, okay, we convert this table, okay, into this type of table. So if you look, it is the same value actually from 0 to 12, okay, 0 to 12, okay, 0 to 12, and then it continues here 14 to 24, right? And then CT 0, okay, to 12 is 5, so 0, 1, and 5, and then continue with 1.5 to okay, 1.5 to 0 back. All right, so in order for us to determine your T bar or your TM, actually T bar or TM, same thing, means residence time, we use this formula. Okay, so if you look at here, it's T times CT dt, integration of integration of TC dt, 0 to infinity, and over divided by integration of CT 0 to infinity dt. So by right, you need the integration is also can be calculated, can be solved using Simpson's method. Okay, I think in your knowledge of what Prof. Dean has taught you before on solving certain reactor design, okay, you've learned on Simpson's rule. Okay, it's just a numerical method. I hope that you know how to use it. If you don't know, please like let me know in the group, okay, in the WeChat group, right? So if you look here, it's T times CT. So that's why we will have this column, right? T times CT. So if you look here, so 0 times CT 0, so that's why it's 0. So this T is 2 times CT is 1, so that's why it's 2. 4 times 4, that's why it's 16, right? Okay, over CT, so this is the column for CT. Okay, this is the column for CT, this is TCT. So to solve later on your TM, okay, so let's look into the next slide. Okay, so I wanted to solve for your TM. Okay, see, this your TM or your means residence time T bar, solving the integration using Simpson's rule that I mentioned before, right? Okay, so this is the formula for the Simpson's rule, where H is actually the gap between your data. So for instance, okay, here the gap is 2, right? 0 to 2, so you can see the gap here is 2. Sometimes some data, they don't have the similar gap. Okay, so you need to like you divide it, the data with using the similar gap, right? So in this case, all the data have the similar gap, which is 2, right? So that's why you see when you have this integration of 0 to infinity, okay, ct dt, so it's 0 to 24 because the time was, the t is only until 24. So you follow this formula. This formula is actually following the Simpson's rule, where h is 2, and then you start to following this is actually the value of your ct, right? This is the value of your ct at a particular time, okay, the one in the bracket. So this 4242 is actually from the Simpson's rule, right? So whereas to find the TCDT, okay, so you refer back, okay, to this value, right? TCDT, okay, so this value. So for instance, let's say at t equals to 2 minutes, your t times ct is 2. So let's have a look. Okay, so all right, so 2 minutes, okay, 2 minutes, okay, this is 2, right? So you just solve this one. You refer to the data, okay, refer to the data following this column. For this column is for t bar, okay, this column as well for t bar, right? So the next one on solving the variance is following this formula, okay, so t square ct dt over ctd, okay. So you solve this one for the Simpson's rule, okay, and then that's why we having this column, okay, t square ct, okay. So for instance, let's have a look on number 2 at 2 minutes, okay. 2 times 2 to the power of 2 is 4 times 1 is, so it's equals to 2 and then times 1, right? So that's why you get 4. So for this one is actually 4 times 4. Okay, that's why you get 64. So you continue up until 24, t equals to 24 seconds, right? And then similarly, you solve all these things with using the Simpson's equation, Simpson's method, this. So it's similar. So this one is actually Simpson's method, okay. Then you solve for variance square, okay, following this formula for variance and then this formula for t bar. So I think that's all for showing you example of 5.2, 5.1 and also example 5.3. Okay, see you in the next part of the video. Bye.